Problems, numerical problems we encounter in feedback amplifiers. They pertain to connecting relations between gain with feedback and gain prior to feedback, input impedance with feedback, input impedance prior to feedback, output impedance with feedback, output impedance prior to feedback, distortion with feedback, distortion prior to implementation of feedback, bandwidth with feedback, bandwidth prior to the application of feedback. In this session, some problems, numerical problems, they are considered, their solutions are provided, and going through the problems and their solutions enhances the understanding level in the topic feedback amplifiers. Analog circuits, feedback amplifiers, problems, series on semiconductor devices and circuits, lecture number 9.13. Feedback is a versatile, sophisticated, self-correcting mechanism or technique. It is being used in almost all branches of engineering. In amplifier circuits, it is used to adjust their impedances. It is used to stabilize their gains. It is used to reduce their noise. It is also used to reduce the distortion. In the present session, we consider several problems and their solutions too, which are set around amplifiers with feedback. Let us move further to start the course session. We begin the session with a problem, example 1. An amplifier with negative feedback has a voltage gain of 100. It is found that without feedback, an input signal of 50 millivolts is required to produce an output, whereas with feedback, an input signal required is 0.6 volts for the same output. Calculate the voltage gain with feedback and also the feedback factor. Without feedback, input signal required is 50 millivolts to give the required output. With feedback, input signal required is 0.6 volts to give the same output. And we are asked to find out voltage gain with feedback and the feedback factor. Solution. Given that gain without feedback is 100. So A is 100, and without feedback the input required to produce the necessary output is 50 millivolts. So without feedback, output is gain multiplied by input. Therefore, it is 50 into 100 equal to 5 volts. With the feedback, the output requires to be same for an input of 0.6 volts. Hence, the gain of the amplifier with feedback becomes AF is 5 by 0.6. This ratio is 8.33. Notice gain with feedback or without feedback. In both the cases, it is output voltage by input voltage or output current by input current. This relation we have used here. AF means gain with feedback. 5 is output with feedback. 0.6 is input when feedback is implemented. So output by input is with feedback. It is equal to gain with feedback. It is 8.33. The first part of the problem is solved. Second part is feedback factor. To find feedback factor, we use the relation AF is A by 1 plus beta A. AF is gain with feedback. A is gain without feedback. Beta is feedback factor. AF is available. A is available. Substituting those available values, beta can be found without much difficulty. In the present case, it turns out to be 0.11. Another problem, example 2. The gain of an amplifier A is 500. Its feedback factor beta is 0.05. Determine A, loop gain or return ratio. B, desensitivity or return difference. C, gain with feedback. D, sensitivity. And E, amount of feedback. This problem is set to test the knowledge of students regarding the definitions of various terms that are associated with feedback. First, we consider A. Here we are asked to determine loop gain or return ratio. Loop gain or return ratio is the product minus beta A. Beta is available given A is available given A is 500, beta is 0.05. Multiplication gives loop gain or return ratio as minus 25. Now B, desensitivity or return difference. It is indicated by D. It is equal to 1 plus beta A. Beta is given, A is given, substitution results D as 26. C, gain with feedback. AF is gain with feedback. We know it is equal to A by 1 plus beta A. But 1 plus beta A is D. Therefore, it is A by D. A is given, D we have already calculated 26. So, gain with feedback becomes 500 by 26 equal to 19.23. Next, D, sensitivity. Sensitivity by definition is 1 by D. D is available 26, so 1 by 26 is equal to 0.038. Amount of feedback, that is E. In decibels, it is 20 log mod 1 by D. D is available, substitution gives us amount of feedback in decibels as minus 28.30. As already mentioned, this problem is meant to test the understanding, the knowledge of students in the definitions of various terms we come across in the study of feedback technique, feedback concept. Another problem, example 3. The gain of an amplifier is decreased to 10,000 with negative feedback from 60,000. Without feedback, it is 60,000. With feedback, it is 10,000. Calculate the feedback factor beta. Also express the amount of negative feedback in dB. It is quite simple problem. We know gain with feedback is gain without feedback divided by 1 plus beta A. Now AF is given 10,000, A is given 60,000. So beta can be determined without any difficulty. In this case, it turns out to be 8.3 into 10 power minus 5. The amount of feedback in decibels, usually it is indicated by N. It is 20 log mod AF by A. AF is 10,000, A is 60,000. So this ratio is 1 by 6. 20 log 1 by 6. It is equal to minus 0.778 dB. Of course, it's also equal to 20 log 1 by mod 1 plus A beta. In this way also one can do it, because 1 plus A beta is available as 6. This way also one can find. Another problem, example 4. The gain of an amplifier is 60 dB and its output impedance is 10K, and it is required to be reduced to 500 ohms by applying negative feedback. Calculate the value of feedback factor beta. Also find percentage change in the overall gain for 10% change in the gain of internal amplifiers. Let us proceed to solve this problem. Given that gain without feedback, it is 60 dB. 60 dB corresponds to a gain of 1000. Now, we use connecting relation between output impedance with feedback and without feedback when output impedance is required to be reduced. That relation is Z0F is equal to Z0 by 1 plus beta A. Z0F is output impedance with feedback. Z0 is output impedance without feedback. A is gain without feedback. We have already calculated it as 1000. So in this relation, all parameters are known except beta. Substituting values of Z0F, Z0 and A in this expression, one can find beta. It turns out to be 19 into 10 power minus 3. The percentage change in the overall gain with the feedback is given by this formula. Mod DAF by AF into 100 is mathematical expression for percentage change in the overall gain with feedback. This is mathematical expression for this statement, for this quantity, and it is equal to mod 1 by 1 plus A beta dA by A mod into 100. So this is what we want. It is product of three terms. Using the percentage change in the gain without feedback, dA by A mod into 100 is, it is given that it is equal to 10. It is given as 10. dA by A mod into 100 equal to 10. So this part is given. Now DAF by AF, its mod into 100, it becomes equal to 10, this part, and mod 1 by 1 plus A beta. It is 5 by 100. Now we get it as 0.5 percentage. Another problem, example 5. The voltage gain of a voltage amplifier is 40 dB. Its input resistance is to be increased to more than 2K from 500 ohms. And output resistance is to be decreased to less than 400 ohms from 3K by applying negative feedback. Mention the type of sampling and mixing to be used and determine the value of feedback factor. It is a voltage amplifier, and it is said that input resistance is to be increased. So the type of mixing is series mixing. Series mixing only enhances the input resistance. Output resistance is to be decreased. So voltage sampling is to be implemented. Only voltage sampling decreases output resistance. So voltage series is the appropriate feedback in the present case. Now solution process. Given the gain A without feedback in dB as 40. So in absolute value, gain 40 dB is 100. A is 100. The required connection, as already mentioned, is voltage series, and to set the input impedance to the desired level, minimum feedback factor required to be used. It can be found as ZIF equal to ZI 1 plus beta A. Using this relation, one can find. This is the expression for input impedance with feedback. When series mixing is implemented at the input terminals. ZIF means input impedance with feedback, ZI input impedance without feedback, beta is beta, A is gain without feedback. ZIF is given, ZI is given, A is available, so beta can be found. It turns out to be 0.03. So a minimum feedback factor of 0.03 is required so that input impedance rises to about 2 kilo ohms. To set the output impedance to desired level, minimum feedback factor required can be found using the relation Z0F equal to Z0 by 1 plus beta A. This is output relation when voltage sampling is adopted. So Z0F is available, Z0 is available, A is available, beta can be determined. It turns out to be 0.065. Notice input impedance enhancement requires a minimum beta value of 0.03, whereas required decrement in the output impedance requires a minimum value of 0.065 for beta, but only one value can be given to beta. By comparing these two, one can understand to satisfy both the conditions, feedback factor beta requires to be more than 0.065. Another problem, example 6. The trans resistance of an amplifier is 100. Its input resistance is to be decreased less than 500 ohms from 2K. Output resistance is to be decreased to less than 400 ohms from 1K by applying negative feedback. Mention type of sampling and mixing to be used to determine the value of feedback factor. Notice input resistance is to be decreased. Therefore, mixing has to be shunt. Output resistance is also to be decreased. So, sampling must be voltage. So, voltage sampling, voltage shunt is the required feedback voltage shunt. Now, we try to solve the problem. Given that trans resistance of amplifier is 100, required connection is voltage shunt as already mentioned, and to set input impedance to desired level, minimum feedback factor required can be found from this relation. This is the relation when you go for shunt mixing. ZIF is equal to ZI by 1 plus beta RM. RM is available, ZI is available, ZIF is available. So beta can be found as 0.03. This is minimum 0.03. To set the output impedance to desired level, minimum feedback factor required can be found from the relation Z0F is equal to Z0 by 1 plus beta A. This is the expression for output impedance when voltage sampling is adopted. Substituting the values, available values, one can find beta equal to 0.015. Notice input resistance, desired input resistance requires beta to be more than 0.03 and required output impedance, it necessitates beta to be more than 0.015. Considering these two aspects, and as we don't have the possibility of having two betas in a single feedback loop circuit, only one beta value we can have. That beta value, it can be easily understood that it should be more than 0.03, more than larger of the two. Example 7, another problem. The maximum current gain of an amplifier is 400. Its input resistance is to be decreased to 500 ohms from 2.5 kilo ohms. Mention type of sampling and mixing to be used and determine the value of the feedback factor beta. Also find its output resistance with feedback when it is 1 kilo ohm before feedback, assuming a load of 5 kilo ohms. This problem may be appearing complex, but it is not that much complex. It is as simple as any other problem we considered so far. Okay. Solution. The current gain under loaded condition. 400 is current gain under unloaded condition. Under loaded condition, it has to be evaluated. It turns out to be AI is equal to A small I R0 by R0 plus RL. RL is load, R0 is output impedance, AI is gain unloaded. So loaded gain, current gain can be determined. It turns out to be 66.67. The appropriate connection is current shunt. Current sampling, shunt mixing. And to set input impedance to the desired level, feedback factor required can be found as RIF is equal to RI by 1 plus beta AI. AI is available. Beta has to be determined. RI is available. RIF is also. RI is input resistance without feedback. RIF is the same with feedback. Now beta can be determined within no time. It turns out to be 0.06. With this feedback factor, the output impedance becomes ROF prime or R prime OF means output resistance with feedback when load is connected. R prime naught is output resistance of the amplifier without feedback with load connected. Prime indicates load is connected, loaded, amplifier is loaded. 1 plus beta AI, small I means unloaded value, unloaded current gain, by 1 plus beta AI, capital I means current gain of the amplifier when loaded. So substituting these values in the expression, available values in the expression, one can find R prime naught F as 4.17 kilo ohms. Here 833.33 is R prime naught. This is parallel combination of 1K and 5K. Another problem, example 8. The maximum transconductance of an amplifier is 500. Its input resistance is to be increased to 2K from 500 ohms. Mention type of sampling and mixing to be used and determine the value of feedback factor beta. Also find its output resistance with the feedback when it is 1K before feedback, assuming a load of 5 kilo ohms. Solution. The transconductance under loaded condition, it is to be computed. GM, G capital M means when loaded, transconductance when loaded. G small m means transconductance when unloaded, multiplied by R0 by R0 plus RL. R0, RL, their usual meanings hold good here. Their values are given in the problem. Substituting, one can find GM as 83.33. The appropriate connection is current series. And to set input impedance to desired level, feedback factor required can be found as. See, for a series mixing, input resistance with feedback, it is related to input resistance without feedback through this relation. RIF is RI 1 plus beta GM. Substituting the values, available values, beta can be determined as 0.036. With this feedback factor, the output impedance becomes R prime naught F equal to R prime naught 1 plus beta GM by 1 plus beta GM. The quantities here have their usual meanings. Notice 833.33 is parallel combination of 1K and 5K. So both the values, feedback factor beta, it is found equal to 0.036, and output resistance with feedback when loaded, it is also determined. It turns out to be 3.96K. Another problem, example 9. An amplifier has a mid-band gain of 125 and bandwidth of 250 kHz. A 4% negative feedback is introduced. Find new gain and bandwidth. B. If bandwidth is to be restricted to 1 MHz, find feedback ratio. Solution. Given that amount of feedback is 4%, it means AF, gain with feedback, by A, gain without feedback into 100 is 4. That is the meaning of amount of feedback is 4%. From this, AF can be determined. 4 by 100 into 125, it turns out to be 5. Now, hence the gain with feedback is 5. The gain bandwidth product of the amplifier remains constant independent of feedback. This is the basic principle based on which this problem is set. Bandwidth with feedback, it becomes 125 into 250 into 10 power 3 by 5. It turns out to be 6.25 megahertz. B. If the bandwidth is to be restricted to 1 megahertz, the gain with the feedback has to be. We are asked to find out feedback ratio if the bandwidth is restricted to 1 megahertz. For that, what we have to do is, the gain with the feedback has to be determined. It is AF is equal to 125 into 250. This is gain bandwidth product without feedback divided by bandwidth with the feedback. It gives gain with feedback. It turns out to be 31.25. From gain with the feedback factor can be computed as follows, like this. AF by A is 1 by 1 plus beta A. 1 plus beta A now equal to A by AF. So 1 plus beta into 125 is equal to 125 by 31.25 equal to 4. From this, beta can be determined. It turns out to be 0.024. Hence, the feedback factor is 0.024. Another problem, last problem. An amplifier has a gain of plus or minus 100 and a distortion of 8%. What is the effect of introducing negative feedback with a factor of 0.05 on the distortion of the amplifier? Here, gain is said to be plus or minus 100. So we have consider plus 100. We have to consider minus 100 too. For both the values, we have to solve the problem. Solution. Introduction of the negative feedback reduces distortion given that A is 100, D is 8% and feedback factor is 0.05. Distortion with feedback then becomes DF. DF means distortion with feedback. It is equal to D, distortion without feedback, by mod 1 plus beta A. It turns out to be 1.3%. Notice, earlier it is 8%, now it is 1.3% reduction, great reduction. This is when we consider gain as 100. If we consider gain as minus 100, then DF can be found as 2%. In this case also there is a reduction, 8 to 2%. These are some of the problems which I want to discuss in the present session. All these problems, these are set around impedance adjustments of the amplifier circuits, distortion reduction, bandwidth adjustments of the amplifiers with the help of feedback. Hope this session is useful to you. We meet again in another session soon with a new topic.